All right, hi everybody, I'm Addison Snell with Intersect 360 Research. Thrilled as usual to be here as part of the HPC AI Advisory Council, and in particular be back in Lugano, which is such a gorgeous location. I've got a great panel here and only half an hour to talk to them, and if we're going to take questions from the audience as well, I'm probably not going to get very many in. But let's talk about we're talking about the future of HPC. As we've done that, we're getting a lot of talks about AI and machine learning, and that's kind of the unavoidable topic here. But what we've been getting so far is a lot of talks about HPC or AI, and not so much topics about HPC and AI. I was just recently at the Rice Energy HPC workshop, which I love going to vertical specific conferences because then you get really specific about what are we trying to do. AI came up there, and it was almost like it was a hammer looking for nails, right? That they were still doing all of their normal work. Yeah, their bosses were geeked out about machine learning, and we're trying to do it, but we're not really sure where it fits yet. So if we're talking about the future of HPC, well, now it's up there as the future of HPC and AI. Are those two different things? Are they going to be the same thing? Let's talk about where they, is this one thing or is it multiple things? What's your view on that? Just start diving in. Mark, you look like you're about to talk. You're right by a microphone. Get in there.
Thanks. So I think we've had some very interesting talks already today. I wasn't here yesterday, unfortunately, and about this convergence. I think my inclination is to try to get away from an either-or and focus on what it is we want to do. So what are the questions that are trying to be answered? And then AI might be the tool that we use for that, or a simulation, or a combination of the two. And I think increasingly that's the way I would see it going, that it's always been like that in the simulation community. You don't essentially start with a simulation and then decide what question you're trying to answer. You have a question in mind, and then you use a simulation to answer it. And I think that if we think about it that way, it'll help to decide what it is we need in each case.
I'm going to double click on that for a second before anyone else goes, because I think that's a great answer, but also an idealized answer, right? Well, sure, that's this nice vision. Are you seeing any of that today? Where are you seeing that already?
So, an example I'd give, which is not answering your question, I realize, but I'll come back to it.
Sneaky panelist.
If you think of exascale, if you talk to researchers, researchers don't want to do exascale computing. They have a problem and it needs computing at exascale. And I think it's the same then with AI, that there's a community developing lots of tools, which is great. We need to be interacting with them a lot more to make sure we don't miss out on something. And there are many examples. So in cosmology, for example, one of the workloads that we support in DIRAC, the use of surrogate models is starting. So essentially AI-trained replacements for the subgrid physics that can't be included. There's also work being done actually using machine learning to solve the equations that are in the simulations. And again, that's the case where the two sets of workloads are coming together. But it's always driven by the fact we have an equation we want to solve. What's the most efficient way to do it? Given, as Thorsten was saying, the industry's driving us in particular directions, so therefore we know some of the hardware that's going to be available. So how can we take advantage of that and AI to do our simulations better or faster or whatever is required to answer the questions?
Who else is dying? Go ahead, Thorsten.
Since my name was mentioned. Yeah, that was a wonderful summary of the state of the art, and I see AI as a tool, and as I mentioned in my presentation, it may be a tool that is getting bigger than the purpose and repurpose for many different things. But one interesting thing that AI helped to actually push is adopting low precision in various fields. So, for example, when I came to Switzerland more than 10 years ago, I was working with the Swiss National Weather Service, Meteo Schweiz, to understand better if we could use single precision for the simulation, because 10 years ago it seemed quite interesting to get twice the performance, right? FP32 versus FP64. I talked to all kinds of climate scientists, production people, and I don't know what, and they all said, no, we can't really prove that it'll work, all the numerics will be unstable, and yada, 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 yada. Then came all these AI people, and it's like, oh yeah, we do everything at low precision, no problem. And then they realized, well, maybe we should just try it. And without any proofs, without anything, just withstanding all of the problems, potential problems, they tried it. And now the production weather forecasting in Switzerland is running on FP32 on GPUs. So as one of the first production services, so very, very innovative in an area that may be moving slower than some others. And so I see AI as a potential nudge. So due to the requirement of higher and more compute, because we scale the models this way, right? This is how OpenAI succeeds and many others succeed. They need to go these extreme routes to extreme performance. I see that we as an HPC field are being pulled by those requirements, and they're nudging us, or by those observation, not requirements. Like we just observe them succeed.
What I like about these two answers is, in the first answer, I heard a lot of the things that HPC was already looking to do anyway. Things like target reduction and mesh refinement have been discussions in HPC for decades, and then we kind of get as a gift this possibility of using machine learning for those parts, and then use my computation in the areas where I want it most. Now, this unanticipated gift of reduced precision, that was never really part of the discussion before. If you ever want to get under a mathematician's skin, say, well, pi is 3.14 and move on, and the mathematician starts going nuts, right? But nevertheless, there are areas where, from an engineering perspective, we're doing some really expensive 64-bit calculation on a model that wasn't that good to begin with, right? You grabbed the mic. Go ahead, Hugo.
That is what we're seeing in several fields, several verticals as well, and sort of like letting loose the FP64 and accepting the FP32 is interesting there. Some other fields that we're seeing is, and that also reflects into the RISE conference, we've done a recent paper, well, a colleague of mine written, he was gracious enough to allow me to co-author it, but to do some seismic imaging on volcanoes, where we actually trained a geophysical model to replicate the simulations that would otherwise be done on a numerical level. And so we see that actually happening. The other ways, of course, defining which parameters to try, multidimensional parameter sweeps. And AI is hopefully going to help there and also lower that amount of compute required.
Now, I'll invoke Torsten's name again here, but I'm going to ask everyone else to reply to something you were saying before, because you were getting into predicting future of HPC, and you were talking about the convergence of architectures, both in networks and in processors, toward what's getting driven by the hyperscale market. Now, with hyperscale, I like to point out that I use that word, not cloud service provider, because I think cloud service providing is one business model that a hyperscale company can be doing, but Facebook is a hyperscale company that's not a cloud provider, and Amazon is bigger than AWS, Google is bigger than GCP. So talking about hyperscale writ large, a lot of this has its origins there and then comes into HPC. You were predicting convergence of those things because of the gravity well of the size of the hyperscale market, which is true. We've been seeing that in our research. I'd like the others to respond. Do you see this converging or diverging in terms of the architectures for HPC and the influence from hyperscale? Are we going to see same technologies or different technologies down the road? We've already got one bet saying they're going to go the same. No one wants to go first.
Sure, let the hyperscaler answer first. At Microsoft Azure, we are most likely converging the most. I mean, the amount of HPC technologies that we already have in the environment is particularly large. I will dive a little bit deeper on that in the afternoon.
Yeah, I think the convergence is going to happen. I mean, mostly from the economical reason. I think that's what I see. Means all the different vendors, as long as you produce like two different things, saying, okay, this is for hyperscaler, this is for cloud, it add more costs and all. So might be the similar kind of product with a little bit different feature sets. That's what we'll see, which can be modified a little bit for the cloud, but in generic manner, it can actually handle all kind of hyperscaler. That's what I feel the direction will be.
Mark?
Thanks. I would agree, and I think the thing we have to do on the simulation side is make sure that even though everything's being driven by AI, that the next generation of systems have at least, let's say FP32, and it's not all FP8 with high latency network. So I think we have to make sure that it's kept in mind what we're doing as well.
Gilad, you've been uncharacteristically quiet.
I'm, Switzerland. But by the way, so for the first question, another example that kind of show the interaction between AI and HPC is digital twins, because digital twins can help to improve simulations models and increase accuracy of different kind of simulations and so forth. So instead of trying to build complicated labs and try to create environment of doing testing, we actually do that on digital twins. Earth 2, it's a good example for that. And AI today can actually do weather forecasting in a very good accuracy for several days ahead of us. So essentially both are being combined and one help the other. On converge of networks, definitely there is a desire to get to one maybe architecture or technology that can use for AI or HPC. In that sense, if that's going to eliminate all the other networks in the world, probably not, because there is different kind of infrastructure, different kind of data centers, different kind of requirements. But definitely things will continue to progress in all fronts. There is convergence, and then this converges, and converges, and this converges. So it's kind of something that continues to evolve over time. Same as disaggregated and aggregated and so forth.
I'll go to the audience for questions here in just a moment, and maybe Brian will help me with that. But first, I'm going to point out that go ahead, Mark, and then I'll...
Yeah, sorry, I was just going to add one thing again, coming back to Torsten's talk earlier, that it's worth bearing in mind that there's convergence now, so it's kind of following on from what Gilad said, convergence now, but it's not clear what AI will need in 5 years' time. And so everybody's requirements are evolving, so it may well converge. And then that's why I would use AI as one of the workflows, or several of the workflows that we consider when we're trying to work out what we need for large-scale computing in general.
Yeah, you set up my comment even better, because we kind of went 5 for 5 down the panel over convergence, and I got to tell you, that terrifies me as an HPC analyst, because here's the thing, we're using this friendly word converge, and I don't think that's the word you mean. I think you mean win, right? We could say that the HPC industry converged on clusters, but what we mean is that SMPs lost, not that SMPs became clusters. These are competing technologies right now. HPC isn't converging toward hyperscale, it's losing to hyperscale right now. Those are, to the extent you're designing one or the other, if people stop designing HPC and design for AI and hyperscale, HPC is going to lose. You can do it on the others, but just on the other architecture, but not as efficiently. Go ahead and re-comment. Hugo, you grabbed it.
I'm not sure that is called losing. I think that both can benefit from that. And we at least are seeing stuff that isn't possible in sort of like local regional data centers. And we're starting to be able to do that at hyperscale level. So I think it's a win.
Okay.
Yeah, I don't think it's losing, actually. I think AI actually helping HPC in that sense. Because if you look, if you trying to figure out what an AI workload needs from a network perspective, definitely not just people talking about bandwidth, but essentially it's more important is effective bandwidth. You can get a network speed at 200 gig or 400 gig, but once you run it in load and in large scale, suddenly it goes down to 50% efficiency. So we need to talk about effective bandwidth, not just bandwidth in a sense. AI does need latency. And we'll continue to argue, and I'll prove in my point. But AI does require latency. Definitely a lot of message rate. So if you take that combination of highly effective bandwidth, and it requires low latency, and it requires high message rate, those are the whole things that also required in HPC. And the race right now for AI, and there is a lot of systems that are going to be built around ChatGPT and stuff like that. That's going to very strong drive the AI systems. We'll see also a fast pace related to HPC because it's going to leverage the same technology. So I think that actually AI helps HPC to accelerate technologies, bring more economy of scale, because optics actually are the expensive part in the system, and you start seeing different kind of technologies that multiple entities are talking about right now that will reduce cost of optical transceivers. With reducing components in optical transceivers, there is work towards co-packaged optics. There is work around silicon interposers, for example, for optics. And AI will help to accelerate that because of the economy of scale. And then we're going to leverage it for HPC as well.
See, Brian asked me to moderate because he knows I get under Gilad's skin. Are there questions out in the audience?
Hi, I would like to hear your thoughts about quantum computing in 5-10 years.
That's a great question. We're talking about the future of HPC. Quantum computing is perpetually 5 to 10 years away. Where are we now? Anyone want to jump on that one? Who's doing it? Anyone doing it here yet? Well, anyone here doing it yet? Hands. Who's doing quantum computing now?
Well, we're exploring it.
Huh?
Exploring it.
Exploring it. Okay, now go ahead, answer the question.
Well, in another 5 or 10 years, we're probably there. But to bring it back, at Azure, we are actually doing it in the sense that we have actual physical quantum computers online within Azure. So we are delivering them as services, but more important, way more important, are the learnings from the mathematical insights that we gained that we're able to apply in scientific codes today, and that have a significant bigger impact than expected. And from that point of view, the learnings from quantum computer are already here today. Hopefully that answers your question partly.
Go ahead, Mark.
Yeah, so we're finding the same in the Dirac community in the UK. So we don't have quantum yet, but we're focusing on training. And so we're running placements with various providers and using a combination of actual hardware and simulators. But we're finding that in areas like radio astronomy and lattice QCD, these are areas where the work that's done on quantum algorithms is actually extremely valuable when it's plugged back into conventional systems as well. And so we're focusing on training because I imagine that at some point in 5 to 10 years, quantum will be something that we need to be building in as accelerators alongside various other accelerators, and it's knowing when the right time is, and that has, for our facility, that comes from the community of users, so they need to have an awareness of what the opportunities are. So that's why at the moment we're focusing on training.
I was about to mention that as something that is new is that we have current generations of supercomputing architectures. The HPE Cray architecture comes to mind, as well as the Atos Pulse Aquana with the BXI interconnect that are both advertised as being ready for quantum accelerators that plug into that. Are we believers in that, non-believers in that? We'll believe it when we see it? Torsten, you kind of chuckled, which earns you a microphone. Go ahead.
Okay, fine. I mean, there's actually I spent some time at Microsoft in the quantum team talking about algorithms and trying to understand what we would do on that front. And it is extremely hard to invent quantum algorithms that give you a speed up on the devices that we are going to see in the next decades, I would say. By decades, I mean about 30 years, maybe. Actually, together with Microsoft, we wrote a paper on that that's going to appear in the communication of the ACM in 2 months. And the upshot of the paper is really that we as a community need to focus on the right quantum algorithms. So many people focus on quadratic speedup algorithms. Like, I know I'm going into the weeds now. I just want to, I like weeds. So the Grover algorithm only gives you quadratic speedup, and if you actually look at the number of algorithms that do that, exactly like kind of medium level polynomial speedup, it's extremely large. Encompasses most of quantum machine learning, if you actually look at it. So you have to be extremely careful what algorithms you look at and what is your I/O requirement in and out of the machine, because quantum computers have a huge problem with the I/O in general. Like just reading any data or outputting any data is a bit of a pain, or extremely slow. So in that sense, I'm completely agreeing with the previous panelists. Yes, quantum had a wonderful I'm agreeing on a panel. That is not a good sign. I do disagree on the latency, though. Quantum had a wonderful impact by dequantizing algorithms, as you mentioned, and it's going to be an accelerator, like a matrix unit we would have today in a unit, like in an NVIDIA GPU. But then we have to find good uses to it. Like for the matrix unit, there was a paper by Satoshi Matsuoka talking about matrix units may not be super useful. Well, we have to find a good use for these units, and that is still in the open outside of quantum chemistry, and now you regret that you asked me, right? I will not stop talking.
No, DK's got the microphone. We'll take him, and then we have time for one more question from the audience after that. Go ahead, DK.
Yeah, I think, I mean, of course, quantum is there, it will come, but I am not very sure about 5 to 10 years. I mean, that particular time frame, I'm not very optimistic. The reason, even if you see AI, I mean, I know we are designing all this machine training, but the biggest challenge is still explainability. I mean, these AI solutions, can we really understand it? Now you go to the next level, the quantum. I mean, that is a much more bigger challenge. I mean, can we really understand what is going on or what is the solution? Unless you have that kind of an explainability situation, then in real life or let's say in industry, I mean, people will not really use those things. That is my opinion. Might be HP has more insights, I don't know. But might be 15, 30 years if I say yes, I think it will happen. But 5 to 10 years might be look too optimistic for me.
DK, that's loud. Okay. DK, what comes first?
Just one, just to...
Fusion reactor or...
Just before going to another question. We need to replace the battery, by the way. So one thing about, just one more side about quantum computing. The belief is that quantum computing will be used as an accelerator for, different kind of algorithms or specific algorithms. And there is multiple quantum computing platforms that were already built, right? There is one in Jülich, for example, and other places. I think right now we're in the era of trying to understand what we can do with quantum computing. And for that you see efforts on creating simulators for quantum computers, quantum computing that runs on GPUs, for example, that help to understand what you can do with quantum computing. From time perspective, probably 5 to 10 years. But right now we kind of are trying to figure out what we can do with it.
Do you have another question, Brian?
No.
Is there another question from the audience here on the aisle?
Hello. I'm a student, so my question might be a bit naive, but I'm still going to ask, take a hit, which is you started with a point where saying HPC or AI and HPC and AI, and about the hyperscaling, even about our hyperscaling. Torsten did mention about the convergence of HPC and AI, but looking into the fundamental concepts of HPC and AI, do you think the point of conversion might be HPC is AI and hyperscaling might help facilitate it?
Yeah, so it's just another way to position HPC and AI. And, you know, to me, I'll give you my view on this and then the panelists can jump in. I think what we really talk about, if we change AI to machine learning for a second, that it introduces just a new computational approach. Most of HPC has been deterministic for years, scientific computing, right? You have variables, you plug them in, you do X times Y equals Z, and you get an answer, and your answer is determined by how good your model was or maybe how good your data is. Some HPC applications have been probabilistic, where, you know, if you were asked, all right, shuffle a deck of cards, and what's the probability that there's some string of 16 cards that contains at least 12 diamonds, that's a very hard math problem and relatively easy to just deal it 500 million times and see what happens. So those are your Monte Carlo simulations, which show up in finance, they show up in genomics, so you have probabilistic applications. This is a third category now that's experiential, that looks at past data and then makes a prediction of new data based on what's happened before, and we call it artificial intelligence because it mimics how we learn as people. You didn't learn how to catch a frisbee by learning physics, you learned it by your experience with how the frisbee moved last time and the time before that. And when you see a cat and you point at it and say, hey, look at that cat, you've never seen that cat before, but you're building on your previous set of knowledge around cats, and that's how machine learning works. And if we just look at it as a third type of computational approach, we ought to be able to fit it in with these others. So to me, it isn't really an HPC or AI thing, but where does experiential computing fit as an approach relative to deterministic computing and probabilistic simulations? But maybe these other guys have a different answer. I think they can work in parallel.
So from the application perspective, I would agree, but from the systems perspective, actually, like how to build computer systems to execute certain workloads.
That's the problem, is those diverge.
Well, I would actually start with the observation that AI is HPC, or used to be HPC, because the reason why AI is so successful is that they used all these HPC technologies out of NVIDIA. They were developed for a completely different purpose. You know, they started with graphics, and then they went to Tesla, kind of like HPC style, and now it's all AI as a business model. So HPC has been the driver for AI, and the big companies hired all my friends and tried to hire me as well to make this happen. So now AI is getting much bigger than HPC, so somehow it came out of that field, at least the large-scale success with large language models. That was all HPC style workload. That was MPI parallelization or parallelization with very similar ilk. And now we are seeing that it's kind of taking over, and from an infrastructure perspective, we shall see what happens. My prediction would be the market will take over, and GPUs will be mostly AI units in the future, and not so much care about HPC, and then we'll see. But maybe there are other predictions on the panelists.
So I think one key thing, which also goes back to the issue about precision of calculations, is that we need to do a lot more work on uncertainty quantification, because that will help us to quantify, can we do things at lower precision? When we do things using a machine learning approach to solve the equations, what are the uncertainties? Because I think a deterministic calculation, in fact, simulations have a lot of uncertainty in them.
Sure.
We just tend to either not talk about it or not quantify it, or hope that if we run the model twice, the simulation twice, and get similar answers, it's probably right. But what we need to do a lot of work, and I know in a lot of fields there's a huge amount of effort going into that, because you want to be able to have actionable conclusions from the simulations. And I think where AI is interesting on that front is we without having explainability, so we know what it's doing. You're right about the catching the frisbee. You learn to catch a frisbee just by catching lots of frisbees, but there's still an underlying law of physics in there. And
Sure.
you won't find that using AI unless we can interpret the AI, and so unless we can really explain what's going on inside it. And that, again, will mean somehow linking, as you said, it's where does that fit into the overall goal of science? And again, I think it comes back to what question are you trying to answer? So if you're trying to just have something that can mimic the act of catching a frisbee, that's fine. If you want something that'll design a spacecraft that'll use the laws of physics, then you have to use a different tool.
An outstanding answer. And what I think the general public needs to understand is that it's not a magic trick, right? And it can't do infinite prediction based on scant. Well, it can. Anything can do predictions based on scant data. It's a question of how accurate things are. And both simulations and predictive science, in a sense, are poor at the things that are truly unusual or disconnected. Chris Willard, my business partner, our original chief research officer, liked to say that when you make a model, it has to be bound in some sense by what's realistic, but reality has no such restriction. So that's our limit, and that's our end of our panel. We're now heading to lunch. Thank you very much for your time. You'll hear more from me tomorrow.
Thank you.
Bum,